Hello, everyone. Welcome to my session today. We're going to be looking at RAG and going into many different aspects of RAG and also sprinkling in some JavaScript at the end, since this is part of the JavaScript AI Build-a-thon. We are going to try and cover a lot of RAG concepts today and see how much we can squeeze in this hour. So hopefully we'll have some questions as you go along, post them in the chat. We may not be able to address them during the session, but we have office hours right after. So you can pop into those office hours and that's where we can address any questions that come up. So I am Pamela Fox. I'm usually doing Python sessions because I'm actually in the Python advocacy team, but I also do love JavaScript as well. So it's fun to get to be in a JavaScript series. I do also spend most of my time on RAG because it is one of the most popular uses of LLMs and where we've seen the most people using LLMs in production. So I'm always excited to talk about RAG with more developers. So let's get into it. At this point, we've probably all been using LLMs in some capacity. And they are incredibly good at some things, right? Like really, really good for coding agents. Like I'm using GitHub Copilot to write almost all of my code now, right? Very, very good at writing code. But they still have limitations, right? They have a lot of limitations. So one of those limitations is that they're trained on data at a particular point and they don't know anything past that point. So people might try to ask an LLM for information and then get back old information, and the LM doesn't even know that that is old information, right? Like if you ask it how to write code using a particular SDK and that SDK has changed in the last 6 months, you're going to get wrong code, right? And then another limitation is that they just have no internal knowledge. So if you want to use an LM to ask about something specific to your company, it's just not going to know at all, right? It was never trained on that. It just doesn't know. So there are some things that LLMs know in their weights because they got trained on so much data that has it and shows it over and over and over and over. And at this point, it's almost a fact. Like nothing is truly a fact in LLM's weights, but almost something it really, really knows without having to look up. Like if I ask an LM how to bake chocolate chip cookies, it knows how to bake chocolate chip cookies, right? It's seen that a billion times. But there's many things that it can't reliably give an answer for. And that's what we want to address. So how do we integrate domain knowledge? There's two primary ways of doing this. The first way is fine tuning, and that's how you can truly teach an LLM. And that's where you take the LLM and you take its weights and you give it a bunch of new data and you retrain the LLM, at least like certain layers of its weights, usually like the outer layers of its weights. You retrain the LLM's weights on that information so that it actually is truly learning that information in the weights. So fine tuning is, a way for an LLM to learn things permanently and keep them in their weights. And it can be good for some really specific use cases where, a general LLM is not doing well. But the problem with fine tuning is that there's huge cost and huge time involved, right? You have to pay to fine tune the model. You need to get thousands and thousands of training data points. You need to spend time fine tuning the model and hope that you've done it well. And then once you fine tune the model, it is more expensive to run a fine tuned model than, one of the general models because it's running just for you. So it can't be optimized as much. So that's why we don't see as many people doing fine tuning. Now, fine tuning could be right for you, especially if in your very particular domain where the LM is really, really struggling with your kind of knowledge and your kind of syntax and questions and all that. But we generally, we don't reach for fine tuning unless we truly, truly need it. Now, what we're going to be looking at today is retrieval augmented generation, which is a way for an LLM to learn temporarily in the moment so that it has enough information to answer a question. Now, you at this point have probably all seen RAG in the wild, right? If you use GitHub Copilot and you ask it questions, it answers based off of what's in your code base and it just searches through it. If you ever use Copilot inside Teams, it's searching on your chats and answering based off your chats. If you're using Copilot inside the browser, like inside Edge, it'll often do a search on the web and then ground its answer based off of the web results, right? So these are all chats that are looking at knowledge and using that knowledge to answer your questions. So how does a RAG start with the very simplest RAG flow possible? So imagine we have a user and the user is asking a question to a car chat application. So the user says, how fast is the Prius 5? So then we use that user question to search a database of car information. And we get back information from this database. And this information has, in this case, it has a bunch of rows and columns with like vehicle, year, MSRP, and acceleration. So then we send both the user's question and all the matching search results to the LLM and say, hey, LLM, your job is to answer this question based off of these search results. And your answer must be grounded in these search results. And you must like cite your sources, right? So we're really trying to tell the LLM like, hey, your job is to answer questions based off this information and not based off of, just what's in your weights, right? So you can even say like, oh, and if something isn't in the information, say you don't know, right? It's actually hard to get an LLM to admit that it doesn't know. I spend a lot of time trying to get LLMs to admit that. You have to like explicitly empower it, right? Sometimes you have to do that with your colleagues too, like, and even myself, like you have to really say it's okay to say you don't know. So that is our simplest RAG flow. And even that on its own is very powerful because we're basically, we're able to answer questions that are grounded in our particular context. So as long as we have a way of searching for the user's question and getting back results, then we can build a RAG flow. Now let's look at what RAG flows tend to look like in production. So, in many of these chat applications, because at this point, a lot of times we interact via chat, usually we're having multi-turn conversations, meaning that we ask a question, we get a response, we ask another question, right? We keep going. Like sometimes I keep going for hours with GitHub Copilot. So here the user says, oh, how fast is it? It gets a response. And then they say, okay, well, how fast is Insight? A different car. So then, we search a database for the most recent question and get back the results. And we send the whole conversation to the LLM so the LLM can get the context of the whole conversation and fill in any gaps based on that conversation. Now, this works pretty well, but we can make this even better. So let's look at this conversation here. So the user asks, how fast is the Prius 5? It gets a response. And then they say, what about the Insight? Now, if you look at this question here, there's a few things to point out. One is that it has a spelling error. Two is that it on its own, it's not a full question, right? It is based off the fact that, first we were saying how fast, and now it's saying what about, right? So it's not a full question. It's missing context because the user's assuming that, oh, okay, well, I'm saying actually how fast is the Honda Insight, right? That would be the full question. So what we often want to do is add in a query rewriting step. So what we do is we take this conversation and we send it to an LLM and say, hey, LLM, here's a conversation. Here's the most recent question. You are going to rewrite this question into a good search query based off the conversation. So then the LLM can take that and say, oh, okay, they're looking for Insight speed, right? So the LLM both, corrects any sort of spelling errors because it's better at spelling than we are. And then also fills in, missing nouns and removes fluff, right? Like, we don't need words like what about the, right? Insight speed, that is all we need to search for is Insight speed, right? So that LLM, its only job is to produce a nice optimized search query that fills in the gaps. So then we take that optimized search query and use it to search the database. And now we're going to get a much better result than if we'd done this original query. What about the Insight? Now we're searching for Insight speed and getting better results. And then we send the full conversation again with those search results to the LLM. So this is the flow that you want to aim for when you are doing RAG for multi-turn conversations. And you just want to generally think in your situation, is this a situation where I would benefit from a query writing step? Now, the drawback of adding query writing is that it does add latency because it is another LLM call. What you can do is you can use smaller LLMs there. You could use like a mini model there. You could even use a nano, but I've seen weird things from nanos. I don't trust nanos. But in theory, yeah, you can use a smaller model for that query rewriting step so that, you know, you're getting it to be a much faster call than your final call. Your final call is going to be your slow call. Your query writing call is generally going to be a lot faster. So this is what you want to think about as a RAG flow when you're designing your systems. The other thing you want to think about with RAG is what kind of data are you searching? Are you searching structured data or unstructured data, right? So structured data is database rows. You might already have an existing database that's got rows and columns, and you just want to have a good way of searching that database. And a lot of databases have built-in search capabilities, but these days, best practice is to figure out what your users are going to be searching for, because usually you'll have some database columns that are like kind of your free text columns that, you know, have a lot of text in them, and that's what users are going to be searching. So in that case, you generally want to be able to vectorize those columns with an embedding model, and then be able to search, you know, the vectorized content of those rows. So often you're going to take your database rows and add in a vector column to those rows so that you can do a really good search for finding semantically similar stuff. Now, with unstructured data, like, you know, PDFs, PowerPoints, Markdown, HTML, images, even there, you need to have a fancier process where you're actually going to take that unstructured data and extract the text and maybe even the diagrams and images from that data, extract that information, split up that information into manageable chunks, vectorize each of those chunks, and then store those in some sort of database or search service so that you can then search it. So these are generally, you know, the two kinds of data sources that you may be doing RAG on, and we're going to explore both of those today. Now, you'll notice something in common is that both of them, I'm recommending that you do some vectorization. So let's talk about vector embeddings. A vector embedding is, it's a list of floating point numbers, and it represents some sort of input, and it represents it basically as a vector in a multi-dimensional space. So you imagine that this vector embedding model, we train the vector embedding model using the similar architecture LLMs, but not exactly the same. But we train the vector embedding model on lots of data, and we show the vector embedding models like the similarity between that data, and it learns similarity relationships, and then it develops this multi-dimensional space where every concept, it maps to a vector in that space. So you have like dog and cat are actually very close to each other, right? Tree and wood would be very close to each other. And then some things are very far apart from each other. And in that space, you can represent single words, but also a lot of these models, you can represent more than single words. You can represent entire sentences. You can represent paragraphs. You can represent more than paragraphs. You can even represent images if it's a multimodal embedding model. So it's this really powerful thing where you can, you know, take these concepts from the real world, and we can try to figure out like what do these concepts look like in a similarity space, right? So that we can then measure similarity between things. And I think it is similar to something like what we do in our head, because I know like with my kids, I often call them by their same name, because call them by each other's name, because in my head, they're like semantically very similar. They're both my daughter. They like, they're both kid. Like they seem similar. So like I just mix up the vectors in my head. And my kids do the same thing to me. They call me by, their nanny's name, right? And they're like, it's fine. It's just we're similar vectors. That's cool. We just mix up our, vectors sometimes because they're too close in our heads. So vector embeddings are very exciting because they enable us to just figure out the similarity between things and search for things that are similar. Now, there are many vector embedding models, and these models differ in how large the input is and what kind of input they'll take. The goal of all of them is to try and capture similarity and build a similarity space. These models also differ in how long their vectors are. So we call that the dimension of the vectors. So so some of them have big dimensions. Some of them have smaller, right? Today, we're mostly using the OpenAI models, text embedding 3 small and 3 large, and those accept up to 8,191 tokens. And a token is the way that LLMs and embedding models understand where it's the way they break up text. It might be a syllable, it might be a whole word. It just depends on what you're feeding in. So they take a bunch of tokens, and then they output vectors of varying length. And you can actually customize the dimensions in some cases here. There's an open model nomic embed text that I use locally a lot as well. And that has really similar performance to the OpenAI models. And then there's also for Azure AI, we have this vision model that can encode images. And that one's really fun. So whenever I want to do stuff with image similarity, I use that AI vision model. So there's lots of models. There's this leaderboard here that you can check out to try and get the look at performance. But generally, you want to figure out, does this model work for my domain? Like, is it representing these concepts the way I expect, right? If I think cat and dog should be similar, is it similar here? So you want to check for your domain, for the language that you're doing, for the kind of input you're doing, image or text. Is it going to work for you? Then once you've decided on a model, then you want to generate an embedding for it. I usually use the OpenAI SDK. So this example code here is JavaScript code that shows how to generate embedding using OpenAI models hosted on Microsoft Foundry. So here we set up our OpenAI constructor. You can pass in a key, or you can use keyless, pass in your Azure OpenAI endpoint from Foundry. And then we generate an embedding. So we say, okay, we want to create an embedding using the text embedding 3 small model with 1,536 dimensions. And here is what we are actually encoding. So here I just put a short phrase, but we can put up to 8,191 tokens there. Now, I keep saying tokens. We don't have time to talk about tokenizer today, but what you can do is search for OpenAI tokenizer, and it's very fun. You can play with it and see, how these models break up the words into tokens. So in this case, it broke each of these up into a token per word. But in other languages like Spanish, it actually breaks it up into more tokens because it has less training data for Spanish. So you can play around with that. If you want to understand, get more of an intuition for what tokens actually are. Okay, so we generate the embedding. Now we want to be able to say, hey, how similar are 2 inputs, right? And to measure the similarity between vectors, there are multiple metrics you can use. The one I'm going to recommend the most is cosine similarity. It works the best for RAG, and it works the best across models. And basically, it is just computing the dot product of 2 vectors and dividing by the magnitude. So you can think of it as measuring the angle between 2 vectors. So this generally works quite well for our RAG use case, and it's kind of the default metric that we'll use. Then how do we actually do vector search? So what we're going to do is we get an input vector. We're getting input, like we have that input query. We're going to turn that input query into a vector, and we need to use exactly the same model that we used to encode our existing vectors. So this is really important, and I get this question a lot. So you have to keep track of what embedding model did you use to encode your existing data, and how many dimensions did you use when you encoded it, because you need to match that exactly when you're then doing a search. Right? Because all of these embedding models have different similarity spaces, and you can't search with across different models. So we turn that into a query vector, and then we search and say, okay, which are the n closest vectors to this input vector, right? And you could do this with brute force. You could just compute the similarity, the cosine similarity between every single other vector in your database. However, once your database gets quite large, then that's going to get quite slow. So you generally do not want to be doing exhaustive search in production. You want to use some sort of approximation algorithm. So you want to use an approximate nearest neighbor search algorithm in order to be able to search millions, billions of vectors and be able to do it in a reasonable amount of time. So these are the most popular algorithms that you are going to hear about. The most popular right now is HNSW, Hierarchical Navigable Small Worlds. And there are JS libraries for that one. But generally, you're going to use it as it's built into a database, right? So often I use like Postgres with the PG Vector extension, Azure AI Search, ChromoDB, Weaviate, like pretty much all the vector databases have support for HNSW. Then there is DiskANN. This is a algorithm that came specifically out of Microsoft Research, which is like really optimizing based off like hardware improvements. And that has support in a lot of the Azure database offerings. So you'll find it in Cosmos DB, Azure SQL, and Azure Postgres. Then there's IVF Flat. And that one's a good algorithm if you're only going to index your data once. It doesn't work as well for repeated updates, and that's why people like HNSW, because HNSW is like pretty fast with handling new inserts into the database. IVF Flat doesn't handle new inserts as well. That's why it's not as popular. But that is supported in a lot of places as well, like Postgres PG Vector. That's where I've used it. And then there's FICE, and FICE is an in-memory index only. So we do have FICE, we do use FICE sometimes for, just prototypes and demos, but not in production. Okay, so I just talked all about vector search, and now, everybody gets really excited about vector search, and they're like, great, I'm just gonna use vector search, and I'm gonna get great results, and that's all I need. But that is not the truth. The truth is that vector search is not enough. And I have a whole blog post titled "Vector Search is Not Enough" because this just kept coming up all the time. So yes, vector search is amazing and will help you answer queries that you could never answer before. However, it is not enough. You should be using more than just vector search. So here's some research that we did at Microsoft, comparing different kinds of search strategies with different kinds of queries. And, vector search did pretty well with a lot of the queries, but it absolutely failed at some of them, right? So keyword queries, if you're searching for exact words, if you're searching for, if I'm searching for my name, exactly my name, then I want to find my name. I don't want to find similar names. I want to find my name and only my name. If I'm searching for my email address or an exact product number, or even any sort of exact numbers, if I'm searching for the number, like I want something that's 25 feet long, I want exactly that. I don't want it to be 75 or 100, right? So vector search really doesn't do well with exact matches. And sometimes users do need exact matches, right? So what we're going to see is that the best search strategy generally is to do a hybrid search, where we're going to combine multiple kinds of search together to get all their benefits and merge them. So hybrid search basically takes keyword search and vector search, merges it all together, and then ideally uses a re-ranking model in order to get the best of the best. Now we're going to break that down so that we understand each step and how they produce the best results. So the first one is keyword search. Keyword search is what we used for years and years before vector search came along, where basically we look at the words in our data, and then we build an inverted index based off the words in there, and we say, hey, this term shows up in these documents. And then when we do a search, we're basically saying, hey, find us the documents where this term shows up the most, right? So you're actually looking at the frequency and saying, oh, okay, based off the document size, this term shows up proportionally way more than in other documents. So that's the general idea of a full text search algorithm. The best full text search algorithm is called BM25. So you always ideally want to be using a BM25 full text search algorithm when you're implementing this. Then we have vector search. We already talked about this one. So, we're doing our vector search, and we're using an approximation algorithm in order to make it more efficient. And, I saw some questions in the chat, like, can you just match dimensions when you're searching vectors? You have to use exactly the same model that you encoded your data with and the same dimensions. So it's really important. So I even, when I'm making my database columns, I even name them after the model and the dimensions. So I remember exactly, how those vectors were made. The next step, once we've done keyword search and vector search, is that we're going to merge those results using this algorithm called reciprocal rank fusion. And that sounds very fancy, but really all it's doing is looking to see at the rank of each of the results in each of the subqueries and saying, and just kind of moving things around based off their relative rank. So it's like, okay, if something was, super high in one and low in the other, then it's going to end up in the middle. If it was high in both, it'll end up high. If it was, middle in both, it'll end up middle, right? So it ends up just accounting for the relative ranks in those results. And then we get those merged results. So, it's not using any sort of model. It's just using math. You can implement this entirely in just SQL math functions. So it's just a bit of math to get these merge results based off their relative rank. The final step that I recommend is to add on a re-ranking model. So a re-ranking model is a special model that is designed for re-ranking. It is actually not an LLM. It's generally a cross-encoder model, which has been specifically trained to look at queries and look at results and then assign a score to each result based off the query. So to say, oh, okay, I'll give this one this score 0.9, right? Very good result for the query. And this other one 0.1, like bad result for the query, right? So we can use this re-ranking model, and that way that will really look at the results according to the query, and it often will, find things that we were missing, move stuff around a little bit. And the nice thing here about the re-ranking model is that because it gives a score relative to the query, we can also set a threshold and say, hey, if we get a re-ranker score that's below a certain score, we are just going to drop it entirely, right? So once you start to look at your data, you can get a feel for like, okay, this is the threshold at which the results are just not good enough. And then you just drop it. Because I think that's really important, because both vector search and keyword search can give noisy results. Because vector search, like if you have nothing similar, it'll still find something similar because it's in a vector space and there's always some vector that's closer, even if it's so far away. And then keyword search can also find, noisy results because, sometimes something might match one of the keywords, but then be completely unrelated, right? So I like that re-ranker step because it can compensate for the fact that both vector search and keyword search can yield noisy results. So this is what the complete hybrid search looks like, right? We get the query. We, in parallel, can do a keyword search and a vector search. Then we fuse them together using RF and then send them to the re-ranking model, which will rearrange them and, also assign scores that we can use as the threshold. Now, the good news is that hybrid search is supported in many databases and many databases on Azure if you're developing your RAG on Azure, right? So in Postgres, you can do vector search using pgvector. You can do keyword search using their built-in module. I will say the built-in module is not BM25, which makes me sad. There's a couple like community extensions that do it, so you may want to bring those in. Then you can do RF just in the SQL. And then for re-ranker, there's actually a built-in function, Azure AI.rank, which you can use a cross-encoder model with, right? So Azure AI Search, they have incredible support for hybrid search. They were kind of the first ones to really come out with it. So they're using best-in-class everything. They've got their own re-ranker model that, works really well for it. So it's super easy with that. There's Azure AI Search. Cosmos DB, which we're using for today's JavaScript example, they do support vector search. They do now have BM25 and RF built in, and they have a re-ranker in public preview. So you can start checking out their re-ranker. And Azure SQL is similar to Cosmos DB, but doesn't have a re-ranker yet. So just when you are, picking your database and coming up with your search stack, do consider, whether you can use the full hybrid search stack. Because especially if you're, dealing with messy data, you really want to have the best search possible. Okay, so now, we're talking about how to search that data. The other aspect is, how do we ingest that data? How do we get our documents and our data in a form that is going to be the most searchable? So if we are, if we're doing a database row, that's pretty easy. We're just picking out the columns and vectorizing them. But for documents, things get a lot more interesting. So if we are dealing with documents, then we need to set up an ingestion flow. So here's an example ingestion flow. We can take the PDF, we could send that to Azure Document Intelligence, which is a service that uses OCR models as well as LLMs in order to be able to extract information out. Then we can send it, use some code in order to split the extracted text into chunks. And we can split that text based off of boundaries or headings. Like, there's many ways that you can split your data up. Different kind of chunking algorithms out there, but generally you're going to use some sort of code, some library in order to split the data into chunks. Then you're going to take each of those document chunks and then generate embedding models. And then finally store the data and the original document somehow in some database that is searchable. So it's a general ingestion flow here. Now, I get the question, why do we need to split documents, right? Because people say, hey, Pamela, like LLMs have these huge context windows now. Like, I'm using like a LLM that has like a million, a context window of 1 million tokens. Like, do I really need to split the documents, right? So first of all, when people are developing RAG applications for their domain, they are often putting a lot of documents in that database. So those, the total context of those documents is generally more than 1 million. If you truly are building RAG for a small data set, then yeah, maybe you actually don't need search. Maybe you can just give the entire document to the LLM, right? You can try that and see. But most people are dealing with, databases that have thousands, hundreds of thousands of documents. And, they need to be able to select across them. But the other thing is that, generally, if we send too much information to LM, it gets distracted. There's been all this research that shows like, okay, even if the LM technically can take in all that context, if you send it to information, it will get distracted by it. This was the first paper about it, lost in the middle, but since then there's been more research. And I even saw a tweet this morning that I bookmarked where somebody looked at context rot. Now we call it context rot, where as the context grows bigger, the quality goes down. So somebody looked at context rot for the new GPT 5.4 model, because that one technically has a 1 million context window, but they basically saw is after 256K, the quality just went way down, right? So you hear that these LLMs have big context windows. Yes, they do, but there's still the quality goes down the more you send. Right. And also you spend more money. It's way more money the more tokens you spend in LLM, and also more latency. So if you can do a search that will get you just what you need and send just that to LLM, then that's going to be, better for your budget, better for your user experience. Right. So that is why we're still splitting up documents, is because we want to be able to send to LLM just what is necessary. Now, since the context windows are bigger, I do think we can make bigger document chunks than we did in the past. I think we can, store maybe entire pages or something like that. But I would still split up documents. Now, I always get asked like, okay, all right, so I know I have to chunk the documents, but how big those chunks should be, right? Now, this is research that we did a few years ago, and I think we should probably redo this research now with the newer LLMs that have bigger context windows. But when we did this research, they checked to see like, okay, how big should the chunks be? And in this research, they found that the optimal size was 512 tokens. So in English, you could think that might be 512 words, but in other languages that, would be different. And then they also looked at where should you break the chunks, right? Where do you get the best results? So they tried breaking just at the straight up token boundary, and that got the worst results. They tried preserving sentence boundaries, and that got better results. And then they tried overlapping chunks so that there would be, some overlap between chunks so that some of it wouldn't appear just in one chunk. And that's how they got the best results. So based off this is now my chunking strategy, is that I usually aim for 500 tokens. And I aim for like a 25% overlap, and I try to preserve sentence boundaries within that overlap. Now, it's like, it's kind of crazy code to write a splitter, a chunker. So I don't recommend that you write your own chunker. I think generally you're going to have better results using other people's splitter. And I say this just because I've written a splitter, and there's a lot of edge cases to think about when you're making a splitting algorithm. But if you want to build your own splitter, but generally I would recommend using someone else's splitter, that's been well tested, battle tested. All right. So we've talked about RAG flows and optimal search strategies and data ingestion. Now, there are other RAG approaches as well that people often ask me about. So I wanted to talk briefly about some more advanced approaches that you may have heard about. So the first one is GraphRAG. This was a Microsoft research project from a few years ago. And the idea of GraphRAG is that when you're ingesting your data, as you're ingesting it, you analyze the data to extract out the topics, the entities, the relations, like all how you're trying to make an ontology of the information that you're ingesting. And then you use that to build a hierarchical graph, a knowledge graph that understands the entities and relationships and topics that are covered by that data. And so then you build that graph, and every time you ingest new data, you update that graph, with whatever's in the new data. And then when you're doing the actual querying, you're querying that knowledge graph, and it's particularly you might be querying at multiple levels so that you're able to answer questions. You're able to answer a wider range of questions because you have access to this knowledge graph, right? So this works like particularly well when you're trying to ask questions that are more high level and that are like asking to understand things at a high level versus like just picking out like, little bits, details from the documents. So this is really exciting and people are very excited by this because of the ability to handle a wider range of questions, like handle the more zoomed out questions, as I call them. However, in practical use, it's very hard to use GraphRAG in production because of how expensive it is to build the graph, right? It takes a lot of time to build that graph. Every time you ingest new data, you have to update the graph. So it's just generally a slow and expensive process to use that. And then when you're doing the querying, it is also a more expensive query. So the truth is, I actually do not know anyone using GraphRAG in production. If anybody is in the chat, please let us know. That'd be really fascinating to find out. That's the thing. So we keep looking into it, and we're trying to figure out how to make it reasonable to be able to use this in production. And there's been various efforts. So hopefully we will have some iterations on GraphRAG that are more practical for production. But yeah, right now that is the kind of limitation of it, where there's just so much time and cost that it's unclear whether it's worth it. Now, there are some things kind of similar along those lines that I do want to mention that you can use in production today. So one thing that you could use is you could use RAG with graph queries. So here, this is an example. There's a repo here that you can look at which does this, and it uses Azure Postgres with the Apache Graph extension with Cypher graph queries. So when it does, ingestion, it is building a graph of relationships between things. So in this case, it's building a graph between products, product reviews, product features, and it's the edges, it's labeling with the sentiment. So it'll say like, oh, this review has a positive sentiment of this feature for this product. So it is building this, this graph of relations between tables in the database, right? And in theory, you could also do this with like a Postgres join, but joins are very expensive, right? If you use the Apache Graph extension with Cypher, you can do these queries and have them execute very, very quickly. So yeah, in this case, we're doing a RAG on a product, like a product store. So it says, I want to buy a headphone that has really good reviews on battery life. right? So it says, okay, you're going to find the products with noise cancellation features and where the reviews have a positive sentiment, that's the edge, about battery life, right? And so then it can execute that graph query, and it can execute quite quickly and get back the responses. So this is, you know, almost kind of like a GraphRAG, but it's a little bit different as well. But you might be able to kind of mix, use it to do something similar to GraphRAG with building the whole ontology. So you can consider that option. You can check out the repo there to see how it's actually implemented in Postgres. And then another similar thing, this is a feature from Azure AI Search. This is their new knowledge-based feature, which does agentic RAG. And this is really helpful if you're trying to search across multiple sources. So basically what this does, it takes in, a conversation, and it has that query planning step built in. So this is using an LLM to do query planning, and then comes up with queries and also decides which of the knowledge sources it's going to send those queries to. So it might say, oh, I think for this query, we need SharePoint and we need Bing, but we don't need our, OneLake and our search index, right? So you will configure all these possible knowledge sources, and it's going to decide which of those it's going to search, and then executes those searches in parallel on those searches, and then merges the result using that whole hybrid search, semantic ranker, all that stuff. And then even has an optional iterative retrieval stage where it uses another model in order to decide, does it have enough information? Because that's often an issue with retrieval with complex documents, is just not getting enough information. So it reflects on those and uses another model to say, okay, do these results help us fully answer the question, or do we need to do one more search, right? And that particularly helps with like questions that kind of have dependencies in them, like these more complex questions. And so then it can do that loop again. So that's exciting if you're dealing with searching across lots of different data sources that are unstructured documents, where it just makes it easier to be able to fan across all of them. Okay, so how do I showed all these different search techniques, these more advanced techniques. The question is, how do you know if you are getting good results? How do you know if it's worth it to do GraphRAG, if it's worth it to do hybrid search, right? You need evaluation. And you need this because there's so many things that affect the quality of a RAG flow, right? Like I showed all these different search options, data ingestion options, big decisions there, small decisions there. Every single thing affects the quality of those search results. And then there's the LLM itself, right? What system prompt are you using? Which model are you using? The model has such a big effect, right? The temperature, like so many different parameters. So there's so many things that affects your answer quality. And if you just change one of these, then your answer quality could go up, but it could also go down, right? And the other thing that can go up and down is your cost and your latency, right? Like a lot of this is about latency and cost, right? If we had infinite time, we could have perfect RAG, I would say, maybe. But we don't have infinite time, usually. We're trying to get an answer to somebody who wants it. And so we always have to think about the trade-offs of cost and latency and whether we're getting good enough quality. So what does it even mean for RAG answers to be high quality, right? So are they correct? Are they understandable? And are they formatted correctly, right? So there I've got like 3 different answers here, but there's only one of these I like because only one of these answers has the citation in the correct format that I can then render the citation to the user, right? So, we're looking at all of these aspects when we're thinking about quality for RAG answers. Now, you can do different kinds of evaluation. You could do manual evaluation with humans, and you can set it up so that humans can look through a bunch of answers and they can say, oh, this one's good, this one's bad, and ideally annotate why it's bad so that you can improve. And so this is really helpful to do if you have humans who have domain expertise. But there's a limitation to how much data humans can process. So what you really want is to also set up automated evaluation, based off what the humans discover and annotate, to say, okay, we're going to measure performance and measure these metrics across huge data sets for multiple metrics. There are various automated evaluation frameworks. Typically, I'm working in Python, so I use Azure AI Evaluation. There's a lot of Python frameworks. For JavaScript, there's PromptFoo. I think that's the most popular one for JavaScript. But all these frameworks do pretty much the same thing. They do very similar things. they basically, a lot of them just make it easy to run evaluations across bulk data sets, right? And a lot of these evaluations use an LLM as a judge to score the output. So we're actually using LLM to score the result from another LLM, which is funny, but it works. So, hey. So for example, when we're looking at RAG, we often look at, okay, how grounded is the response? Was the response actually grounded in the data? How relevant is the response to the query? Like, did it answer everything in the query, or did it leave something out? And then we also look at how similar is the response to the ground truth. So if we have the ground truth for an answer, then you can run the best evaluations, because you can say, hey, this is what I wanted. This is what I got. How, did I get what I wanted, right? And I often look specifically at whether the citations match, and that I even just use a regex for. So you don't have to use an LM as a judge for everything. Sometimes, you can use a regex, like when it comes to citation checking, but this is generally the kind of metrics you're looking at. And you can use an LM to judge metrics if that's helpful. So then you're going to run evaluation across these large data sets and keep track of your metrics, right? So, your LLM metrics like groundedness, relevance. Here I have my citation metric, whether citations match, that's my regex. I look at answer length because that varies so much across models. And I usually also look at latency. So it's cut off here, but I always look at latency as well, because you might have better quality, but your latency might go way down, right? So you want to look at all these metrics and also look at length, cost, latency, so that you can really evaluate holistically. And then when you see that scores have changed, I do recommend looking at the specific answers to understand why they changed, how they changed, and whether you need to improve your prompt or maybe even change your judges, right? So I've run lots of evaluations, and I always learn when I run evaluations, and I just think it's so helpful. So you really got to set up evaluation for any of your apps that are based off LLMs. And I think you'll learn so much from it. Hamal Hussein is my favorite person in the evaluation space. Do subscribe to his blog. You'll learn so much about evaluation from him. Okay, we have 7 minutes left. We are going to do a code, look at the actual code that you can deploy that will make a RAG app with JavaScript. So this is a open source RAG solution. And let me go ahead and put this link in the chat so that everybody has it here. Here we go. So this is a open source RAG solution that you can deploy to Azure, and that you can also run locally. So you can run locally using a Ollama and Feist, or you can deploy it to Azure, where it'll use Azure OpenAI, Cosmos DB, and Azure Functions. So here I have it running. So I've already asked a question earlier today, like, okay, what is the refund policy? Let me just reload it. Okay, what is the refund policy? And you can see that the answer will come streaming in. It's also loading my chat history. So it does have chat history. The answer streams in. We get a citation. That's really important. I click on the citation and we can see the actual document that answers the question, right? So this is, what we're building here, which is what you should expect out of RAG application, is the ability to have multi-turn conversations that stream in the results and give you citations and a history of your chats. Now, to get started with the project, you can open it in GitHub Codespaces, which will have everything set up, or VS Code with the dev container extension, or just your local environment where you need to have Node, the ACD CLI, Azure Functions, and Git. So this information is all in the repo. Then you can deploy it to Azure using the Azure Developer CLI. You'll need an Azure account for that and some permissions. You log into your account and you run AZD up, and that'll get everything up on Azure. Now, let's look at how this code actually works. So there is a data ingestion process that's in documentspost.ts, and it is an Azure function. So everything here is deployed to Azure Functions. So this is running on Azure Functions. So we send a PDF to the Azure function. We post it to the Azure function. It uses LangChain.js to both do the extraction. So it's actually doing extraction just fully in JavaScript, and also using LangChain to split the data into chunks. LangChain has a nice character splitter. So I actually, let's see, I have that open here, right? So first we use the PDF loader, and then we use the recursive character text splitter. This takes lots of options here. This code is actually splitting based off character count, but there is an option to split based off tokens, and that's what I usually recommend. So then we split into chunks. Then we generate embeddings using either Azure OpenAI with Cosmos DB or using Ollama with Feis. And then we upload the original file to blob storage, and that way we can have these citations. So that's the full ingestion flow here. You can see that it takes advantage of built-in functionality from LangChain so that the actual ingestion code is quite short. Now, how does the app work itself? This is what it looks like. The front end is TypeScript, and it's built using lit components and byte. And the front end sends post requests to the back end, which is on Azure Functions. So the front end is hosted on Azure Static Web Apps, so it's fully static, and it sends all its API requests to Azure Functions. So the main file is chatspost.ts, which handles the full RAG flow. So let's check that out here. Chatspost.ts. Okay. So this has, actual function. We've got the system prompt here, and notice the system prompt, says you have to answer only with the information from the sources below. It says how it's going to cite the sources so we can pull it out later. It says how to do follow-up questions, right? So here's our actual function. So, we set up our connection to Azure OpenAI and Cosmos DB, and Cosmos DB is being used here both as the vector store and for the message history. So we're using Cosmos for multiple uses here. Locally, we can use Ollama and Feis in memory and a file system message history. Then we use LangChain to chain our documents with our system prompt and our recent human message. And we use this runnable with message history in order to add in the chat history from this current thread. Then with the retriever, we say we're going to retrieve 3 documents from there. And then we run that RAG chain as a streaming function so that we stream back the results and stream it back to the front end. We also make a title for the chat session. That's just for chat history. And then here we go. We return back the stream. So that is the RAG flow. A few notable things here is that it's using Cosmos DB only with vector search. It's not using hybrid search. There is support now for hybrid search in Cosmos DB, as I mentioned, but I don't think it's merged yet into LangChain.js. And this code here brings in everything from LangChain. So hopefully in the future you could port this to, or we port this to hybrid. And yeah, but then we get back some good results there. So that's the code. We encourage you to try out this app. You can try it locally. You can try deploying it. And then what's really fun is to try and customize it for your own data, right? So, put your own documents in the repo and ingest those documents and, see what happens, right? You really only, in my experience, you really learn the most about how RAG works when you do it on data that right? The issue is if you do it with our sample data, there might be hallucinations and you wouldn't even know. But if you do it on data, so I actually, I have a RAG that's just on my blog, right? So I took all my blog posts, ingested those, and then I can ask questions on my blog. And I know what I've written on my blog. I know if it's hallucinating something, if it's not from my blog. And so that has been really helpful for me to be able to reason about how to improve RAG quality, right? So I do recommend deploying RAG for your own domain data so that you really get a good understanding of it. Now we call this a deep dive, but it's really hard to do a true RAG deep dive in an hour. I tried to cover a lot of aspects of it, but honestly, there's so many aspects of RAG and I couldn't fit it all in an hour. I did what I could, but I have an 11-part series that I did last year. And this is with our Python solution, but a lot of the concepts are similar, right? Talking about multimedia, user login, data access control, chat history, speech input output, private deployment, evaluation, monitoring, and extending with function calling. I would love to do an update of this series sometimes because now, it was a year ago and that was ages ago. But there's more things there you can check out. And then, yeah, hope you join us in the Discord afterwards for office hours so that we can answer your questions.